Welcome to the second week of this course. We are moving into our fourth lecture. In the last week, we have seen about fundamental aspects of instruction pipeline, and we have seen how a basic instruction pipeline works and how pipeline hazards are being handled. Now we slowly move into the storage aspect of a microprocessor. We will be taking some time to understand about cache memory, and later on we will move into DRAM structures. So, our fourth lecture is Introduction to Cache Memory. This slide will give you an idea what is the relative growth in the processor industry with respect to the performance of processor and the performance of memory systems. So, what you see in green color here is the DRAM structure, the main memory structure, and what you see here is the performance of processors. You can see that across the years from 1980 up to 2000, the performance of CPU has drastically improved, whereas the performance of memory, even though they are improving, it is not up to the same rate as that of the CPU. This led to a widening of gap. That means, if some activity that is happening in CPU like decoding of operation, performing an ALU operation, these things will be relatively very fast, but whereas activities like instruction fetch and memory access will be relatively slow. This led to an imbalance in the speed of operation of processor related activity and memory related activity. To mitigate that, a hierarchy of memory structure was being proposed. So, this is the instruction pipeline we have seen in the last week, and we can see that there are two stages. One is the instruction fetch stage and the other one is in the mem stage, where we are accessing memory. Our basic assumption of this instruction, this 5-stage instruction pipeline was, every stage will take exactly one clock cycle. We have an instruction fetch, decode, execute, mem and write back. They all are going to take one cycle. Practically speaking, if all the stages, if they have to complete their operation in one cycle, that means the associated circuitry that carries out this operation should also complete its functionality in one clock cycle. Since certain activities are completely happening inside the processor, like what is happening in the ID stage and in the EX and write back stage, it is completely happening inside the register file or functional units. A faster processor will help you in carrying out this task at a very small amount of time. But when it comes to instruction fetch and mem access stages, it is not only the processor that is involved here, memory stage is also equally important. The memory that has to supply the instruction or data has to be equally fast in order to get things done in one clock cycle. So, the main challenge is design of instruction fetch stage and mem stage such that it also go along with the normal pipeline speed. So, what is the role of memory? Programmers always want unlimited amount of fast memory, and what we are trying to do with the help of a memory hierarchy is to create an illusion that we have very large memory and very fast memory. Typically, the requirement of a programmer is programmer want unlimited amount of memory and it is very fast memory. Even though our memory is not unlimited, we create an illusion that memory is very large and it is fast as well. So, how it is being done? It is done by implementing your memory as a hierarchy, and we have multiple levels of memory with the different speeds and sizes, and the entire addressable memory space is available in the largest, slowest memory. When we talk about largest memory in this context, it corresponds to your main memory. And what we typically do in the case of a hierarchy memory, keep the smaller and faster memories close to the processor, and the slower and large memory is after that. So, in a memory hierarchy we can see that we have the fastest memory is available inside CPU as the registers, then we have multiple levels of cache memories with varying size and varying access speeds. and then we have main memory, and then we have the disk storage. As we move from CPU registers into the main memory, we can see that the amount of memory size, the size of memory increases, and the access speed also increases. These numbers will be slightly different when you take the modern cache memories, where it will be of at least one order magnitude larger than what is already present here. Now, what is the concept of a cache? What we do in the case of a cache? We can see that your cache memory consists of two types of cache. In the first level, that is, your instruction pipeline is going to interact with your instruction cache during the fetch stage and data cache during the mem stage. We have seen that in order to avoid a structural hazard, if you have separate first level caches, one dedicated exclusively for instruction and one dedicated exclusively for the data. So, that is called your instruction cache and data cache. They have separate read and write access ports, and then we have a unified L2 cache. It is like one level of L2 cache, and then we have your main memory. This is the way your hierarchy is organized. So, you have a very high speed register file, and then we have a relatively slower L1 cache, the level 1 cache, then when we have L2 cache, and then we have these main memory segments. Now, the introduction of cache memory. What is cache memory? Cache memory is a small, fast buffer kept between your processor and your main memory. The principle that is used in cache memory is old values will be removed from cache to make space for new values, and the entire cache memory is being built on top of principle of locality of reference. We will try to understand what do you mean by principle of locality of reference. Principle of locality of reference itself is defined with two submodules. The first one is called temporal locality and second one is called spatial locality. We will try to understand what do you mean by temporal locality. Consider the case that you are going to access a memory location now at time t. The probability of re-accessing the same location in the near future is very high. Typically, programs has loops, or we have control structures which help us to come back to the same line again. Many programs use these kind of control structures. So, the idea is there is a very high possibility that a location which is accessed at time t will be revisited at time t plus delta t in the near future. And that concept and that phenomenon is called principle of temporal locality. Now, principle of spatial locality says that if a location L is accessed in time t, then the probability of location L plus delta L to be accessed in time t plus delta t is also very high. That means, if you access a location now, its nearby locations will also be accessed in the immediate future. So, these two concepts are being defined by principle of temporal locality. If an item is referenced, it will tend to be referenced again soon. If an item is referenced, items whose addresses are close by will tend to be referenced soon. Now, we will try to see in what way these two concepts are used in the implementation of cache memories. So, when CPU requests for a word, its address is being passed to the memory system. Now, the memory system has to respond back with the corresponding word CPU has requested. If for the very first time the requested word is not available, CPU will give necessary instructions such that the word is being taken from the main memory and it is given to CPU. If we know that programs exhibits temporal locality, so whatever word CPU has requested at this point will be re-requested again in the near future. So, our idea is, can I have a relatively faster memory such that for my next request I should not go to main memory. So, if I have a very fast buffer where the currently request word is kept, its subsequent requests can be serviced from this fast storage. So, we are making use of the principle of temporal locality in such a way that future access to the same location can be serviced from a faster memory. The second principle, the principle of spatial locality, says that if a word is requested now, its adjacent words will be needed in the near future. So, whenever I am going to bring a word from main memory, I know that in the near future, adjacent words from the main memory also will be requested. So, when those adjacent words are requested in the near future, why should I go to main memory? Can I service it from a faster storage? If I need to service that from a faster storage, then when the previous word was accessed, rather than bringing only the previous word, I should bring a bunch of words. So, we are making use of the concept of spatial locality under context that if a word is referenced now, we are going and bringing it from the main memory. When we bring the word from main memory, adjacent words are also. So, we bring a block of words, a block of data or block of instruction is being brought together and kept in this fast storage, and that fast storage is what we term it as cache memory. So, cache memory holds currently accessed data with a hope that it will be re-referenced soon, as well as cache memory holds adjacent data of the currently referenced data with a hope that there will be access to the nearby location. Now, consider this access pattern where we can see the x-axis is your time and y-axis is the various addresses that is being accessed. So, as we can see that when we move across time, different addresses are being accessed and some of the addresses are being revisited. Especially this here, we know that as the time proceeds, we are actually moving into different address. The more we move in y-axis means we are moving across different axes, means the requested words are from different address. When we come back to lower y-axis and going again, the meaning is addresses which are requested in the near past are being re-referenced again. So, this is a perfect example of temporal locality, and we can see that as time progresses, we get lot of spatial locality. So, we get temporal locality and spatial locality. So, consider this example. Let us say all these English alphabets correspond to an address. In the word Mississippi, many times I and S are being repeated. So, a word that is accessed once is being re-accessed again. So, when we are going to access this particular word, this English word, these letters which are accessed once, it will be there in your cache memory. So, when you want it for the next time, it can be serviced from cache. This is a perfect example of temporal locality, and whereas this is a spatial locality. When I access the letter A, in the near future B is accessed, then C is accessed, then D is accessed. So, coming back to A, that is called temporal locality, and accessing adjacent location is known as spatial locality. So, you have your main memory. From main memory, due to the spatial locality principle, we transfer a block of data into cache, and from the cache we will transfer only the word that CPU is asking. So, it is basically word transfer. We will now try to see what are some of the common terms that is being used in the case of cache memory principles. So, the first one is about block or a line. The term block and line are basically same in the context of cache memory. It is a minimum unit of data that you bring from the next level. So, if a data is present, either a block is present or a block is not present. Minimum unit of information that can be either present or not present in a cache level. Next term is called hit. An access where the data requested by the processor is present in the cache, we call that access as a hit. So, whenever the requested word is present in your cache memory, we call it as a hit, and if it is not present, it is known as a miss. Now, what do you mean by hit time? Time to access the cache memory block and return the data from the processor to the processor, that is known as hit time. So, once you give the address, it will take some time to go into the corresponding cache memory to see whether it is present there or not, and then return if the data is already present, and that much time is known as hit time. And hit rate or miss rate, it is actually the fraction of memory access found in the cache, that is called hit rate, and the fraction of memory access which is not found, it is known as miss rate. And miss penalty is the time to replace a block in the cache with the corresponding block from the next level. So, this is going to be the sequence. Once CPU gives an address, I find out to which block the address belongs to, search whether the block is present in cache memory. If it is present, you return the corresponding word. This much time is called hit time. If it is not present, then you invoke necessary mechanism such that you go to next level of memory, bring a block of data. So, replace the existing block where you encountered a miss, bring the new block, and then you are going to continue with the word that processor has requested. So, this is the general cache CPU interaction diagram. So, inside your CPU you have few registers, they are very tiny registers, can accommodate only one word. So, very fast CPU register has room for, say for example, 4 byte words. So, each of these register, for example, can assume 4 byte. So, we will case the case that one word equal to 4 bytes, 32 bit. It is a property of processor. When you vary from when you move from one processor to another, the word length also varies. Now, when you consider the cache memory, it is a small L1 cache that has room for 4 word blocks. So, each of these line or block can accommodate 4 words. So, you have 2 such lines in this case or 2 such block in this case. And when you go to the main memory, it is big, it is slow, but it has room for many 4 word blocks. So, here you have 2 4 word blocks or 2 4 word blocks can be accommodated in cache, and many 4 word blocks can be accommodated in the main memory. And you have to understand that there is what is going to be the unit of transfer. When you transfer something from main memory into the cache, the transfer unit between the cache and the main memory is always in terms of block. And here we know that one block is of 4 words. So, together 16 bytes are transferred together. So, any access to main memory will bring 16 bytes of data, and that is what we call it as a cache line or a cache block. But the transfer between the cache memory to the processor is always in terms of a word. So, processor requests for a word, and if the word is present, cache memory will return the word. If it is not present, you go to main memory or the next level of cache memory. For the time being, we will assume that we have one level of cache and main memory. So, if the requested word is not present in the cache memory, then we go to main memory, bring a block of data. In this case, we are bringing multiple words together, and then you are putting it in the cache, and then we resume the operation. We will see what is a general organization of a cache. Your cache memory is an array of sets. This is what we know as a set, set 0, set 1 like that. So, you have many sets in a cache, and each set can have multiple lines. A set can accommodate multiple lines or multiple blocks, and each line can have multiple bytes of data. So, each of the set has multiple byte of data that is been stored, and then we have a control structure called tag. Few bits will represent your tag, and then you have a valid bit. This is the minimum set of bits that is required in order for a general organization of a cache. So, I will repeat, cache memory consists of multiple sets, each set consists of multiple blocks, and each block consists of multiple bytes of data. And typically, all these, that is the number of sets, the number of blocks per set, and number of bytes per block, all will be multiples of 2. So, in this case you can see 2 power s, 2 power small s, which is equal to capital S here, that is the number of sets. Here you have E lines, here you have B bytes of data. So, what is the total cache size? It is the B into E into S, that is your total cache size. So, when I talk about 64 kilobytes of cache, then that means the 64 kilobyte of cache is divided into multiple sets, S sets. Each set has E lines and each line has B blocks of data. Now, how are you going to address the cache? Once CPU gives an address, how will you know where in the cache it is located? So, when CPU wants an address A, this address A, let us say it is a 32-bit address. This address A, we will assume this is called a physical address. This address A is divided into tag bits, index bits and offset bits. This block offset, set index and tag. There will be T bits for tag, there will be S bits for the index and there will be B bits for the block. Remember, this T, S and B are the ones we have seen. So, this S corresponds to the total number of sets here. So, if we have 4 bits in the index, that means this particular cache memory have 2 power 4 sets. If you have 8 bits in the offset, then each of the block have 2 power 8 bytes of data, and whatever is remaining out of the total bits address, that is what is called your tag. Now, the word at address A is in the cache if the tag bits in one of the valid lines in set index matches with the tag. So, like I have already mentioned, your cache memory has a block of data. Now, for each block we have few bits, let us say 15 bits or a 20-bit tag. So, once you get an address, you have to find out what is the index. From the index, you go into the corresponding set and see whether the tag portion is having the most significant tag bits that is given in the address. And once you identify that your tag is matching, that means your data is somewhere present here. Now, how will I identify? Since there is multiple bytes there, the offset bits will tell you from among this entire block from which byte onwards your word is located. Now, addressing this cache, so this is the steps that is been involved. First, locate the set based on a set index, locate the line in the corresponding set which matches with the tag. So, there may be multiple blocks that is present in a set. So, we have to compare the tag values of each of these block, and if one of the tag value is matching, then that data blocks contains your data, but remove that to extract the data you are using the offset bits. So, your valid bit should be 1, your tag should be matching, and apply offset, you will get the data. But the peculiarity is, in the case of a cache memory, we are not going and performing this comparison on all the sets of the cache. From the given physical address, few bits in the physical address which correspond to set index, that will tell you which of the set where I have to perform these operations. So, that will restrict our access to one of the set. Once you go into the set, perform the stack comparison in all the blocks present there and check whether the valid bit is equal to 1 or not. So, deleting an entry from the cache means making the valid bit back to 0. Now, when you design cache memory, there are 4 important design choices. The first one is, when I bring a block from the main memory, where will I keep? Where can a block be placed in the cache? And that is what is known as block placement. The second one is, once CPU gives an address, how will I know that address is present in the cache memory? And that is what is known as block identification. Here upper level means it is cache. The third one is known as the addressed block is not present. So, you have to go to main memory and bring the block. When I bring the block, where will I keep? That is what is been given by block placement. But when you have multiple possibilities, when you have multiple locations, multiple target locations where I can potentially keep my incoming block, one of this block existing has to be removed. That is what is known as replacement. So, from among many blocks, one block has to be chosen, it has to be taken out, giving way to the new block, and that is called block replacement. And the last one is, when you write on a cache, you can have a write miss. Since the operation is write, CPU has done the storage, it is going to write to memory. The desired memory location is not in cache, so I have two choices. Either I write directly into the next level, or I bring the corresponding block from main memory into cache, perform the write only in cache. Based upon that also, we have different choices of cache memory. So, that is what is known as write strategy. So, to summarize, we have a block placement that will tell you where a block is to be kept. We have a block identification that will tell you once you have an address, how will you know whether it is present inside cache memory. And third one is, when you are going to bring a block into cache memory, which among the existing block is going to be replaced, that is called block replacement. And the last one is, what is the strategy that is to be used when you are encountering with a write miss, and that is known as a write strategy. Let us see each one. The first one is known as block placement. We will now see what are the different types of block placements. Consider the case you have a main memory that is having 32 blocks, block 0 to block 31, and you have a cache memory that can accommodate 8 blocks, given the name block 0 to block 7. In this category of cache memory, the technique that is used is, what is the block number of main memory that is mapped to a specific block in cache memory, and the mapping function is the modulus function. So, if you have block number n to be mapped to a cache memory with L blocks, then it is n mod L. In this case, we are talking about block number 12. So, we use 12 mod 8. Why 8? Because our cache memory has total of 8 blocks. So, 12 mod 8 is 4. That is the reason by which your 12th block in the main memory is mapped to the 4th block in cache. Consider the case we are going to talk about the block number 16. So, we have to find out what is the mapping of block number 16. So, block number 16, as per this function, 16 mod 8, and that is going to be 0. 16 mod 8 is 0. So, block number 16 will be mapped to the 0th block. Similarly, 24th block also will be mapped to 0. Block 0 will also be mapped to 0. Block 8 will also be mapped to 0. So, we may have multiple blocks in main memory that may be mapping into the same block. We will deal with this case later. Now, for the time being, for every block in main memory, there exists a unique block in the cache, and that is known as directly mapped cache. Another category of cache where the same cache of 8 blocks is going to be reorganized in a different shape. These 8 blocks are grouped into 4, where each group has 2 blocks. So, we call it as set 0, set 1, set 2 and set 3. Now, the modulus function is block number in main memory mod 4. Why 4? We have 4 sets. Previously, we had 8 separate sets. Here, we have only 4 sets. So, 12 mod 4 is 0. So, 12th block will be mapped to block or set 0 inside your cache memory, and set 0 has 2 lines in it or 2 blocks in it. So, you are free enough to keep the contents of block 0 in the main memory in any of the block in set 0. Similarly, let us say I will consider about 21. So, 21 mod 4 is 1. So, the contents of block 21 can be kept anywhere inside set 1. Set 1 has 2 blocks. So, you can keep either in the first block of set 1 or in the second block of set 1. This kind of a mapping is known as set associative mapping, and this is known as two-way set associative because each set has 2 ways. I can also organize the same cache as 4-way associative. This 8 blocks is divided into 2 groups, set 0 with 4 blocks and set 1 with another 4 blocks. Since each of the set is having 4 blocks, we call that case as a 4-way set associative cache. So, caches can be either one-way associative, which is known as your direct mapped cache. So, all caches are basically set associative caches. If the number of blocks in a set is 1, we call it as a direct mapped cache. If the number of sets is equal to 1, that means all blocks correspond to one set, then we call it as a fully associative cache. So, in the case of a fully associative cache, there is no restriction, a block can be placed anywhere. So, we learned about 3 different types of cache. Generally, we can call all caches are set associative cache, but to be very specific, we have a direct mapped cache where associativity is equal to 1. We have a fully associative cache where associativity is equal to n, where n is the number of blocks. Now, cache mapping and block placement. Caches are direct mapped, like what we have seen. Block can be placed only in one location, and block number modulo number of blocks in the cache will tell you where it is to be kept. Second one is called set associative. Block can be placed in one among a list of locations, and block number modulo number of sets, that is the difference here, number of blocks. And third one is it's fully associative, a block can be placed anywhere in this cache. So, it is a design choice. A cache memory should be designed as a direct mapped cache, a set associative cache, or a fully associative cache. Now, direct mapped cache, it is the simplest kind of cache, it is easy to build, and since for each of the memory address that CPU is giving, there is only one unique block in cache memory where it can be present. If it is present, it will be present only there. So, only in that particular block you have to go, and in that block perform tag comparison, and if so, it is a hit. So, it is characterized exactly by one line per set. Now, we will see how will you access a direct mapped cache. So, the set selection, once CPU gives the address is split up into tag bits, index bits and offset bits. Let us say the index bits value is your 5-bit is used in this example, and the numerical value of this 5-bit correspond to 1, that means what I am choosing is set 1. So, when I get an address where the index portion correspond to 00001, numerically it is 1, it can go up to 31. The value can range from 0 to 31, that means I have 32 sets in this cache, 2 power 5 is 32. If the address is this, then it is going to set 1. So, first step is going to be indexing, and once your indexing is over, that means you have already reached the set. The next one is called line matching, or it is also known as block matching, and then the extraction of the word. So, block matching means from among the set that we have identified, find a valid block in the selected set with a matching tag. So, what we will do here, first we have to see it is a valid block. The block has to be valid. So, valid bit has to be 1. So, this is the selected block. So, in the previous step we have seen how will you select a particular set. Once a set is selected, look at the valid bit should be 1, and then the second stage is from the given address. Let us say this is the given address, this will represent your tag bits. So, the tag bits say 0, 1, 1, 0. So, whatever is a tag bit that is stored, that is compared with the incoming tag from the address. So, if the valid bit is 1 and the tag bits are matching, this means it is a hit. So, if condition 1, that is valid bit, and condition 2, there is a tag match that happens in the selected set, then we call it as a cache hit in the case of a direct mapped cache. Now, once if it is a hit, then your data can be present anywhere. So, you assume here you have 8 bytes in each of the block. Let us say the offset portion of the address is saying 100, so that corresponds to the 4th block. So, from 4th block onwards, you extract a word, and that is what is the word that CPU is requesting for. So, there are 3 steps that is involved in the accessing of a direct mapped cache. From the given address, find out the index bit. From the index bits, go into the corresponding set. In the corresponding set, search whether the valid bit is 1, and for a line where valid bit is 1, see whether the tag that is already stored in cache memory is same as the tag bits that is given in the address. If that is happening, then it is a hit. That means the requested data is present in this particular block where this tag match occurred. From the offset bits, we will be able to locate what is the beginning point of the data, extract the data. This is how it has been done. One CPU is given an address, you divide the address into tag bits, index bit and offset bits. Using index bits, you reach the corresponding row or set number of the cache, extract the tag value that is already stored there and compare with the incoming tag. If they are equal, we call it as a hit. If it is a hit, then the offset portion will tell you which among the word that you have to replace, and these combinational circuits will help you in extracting your data as per whether it is a hit or a miss. This is an example of a direct mapped cache. You consider a 1 KB direct mapped cache where you have 32 bytes are there in each of the cache block. So, how many sets we have? We have total of 32 sets are there. Now, each set has only one block, that is why it is called a direct mapped cache, and each of these block we can store 32 bytes of data. This is how you store 32 bytes of your data, byte 0, byte 1, etc. up to byte 31. Similarly, you have total of 1024 bytes, that is called 1 kilobyte. This is the way how your 1024 bytes are organized. 1024 bytes are organized 32 byte each in a block, and you have total of 32 blocks. Now, consider in this example, let us say the index is 0, 1. So, I go to the first location. Let us say the tag value is 50. So, if 50 is present, then my data is present somewhere here, and this is used to extract. So, this byte 32 is going to help me in finding out the data. Now, we will see in the case of another category of cache that is known as set associative cache. We have seen earlier that set associativity means the entire cache memory is divided into multiple sets and each set has multiple blocks. So, in this case, I can see I am dividing it into multiple sets and each of the set has 2 blocks each. This is known as a two-way associative cache. Now, how will you access? From the given address, again we are going to the index bits. Here also my index value say it is 1. So, I go to set number 1. Once you reach set number 1, then we have to see block matching is done exactly same like a direct mapped cache. So, block matching is done by comparing the tag in each of the valid line. So, you see whether anything is valid. So, here both the blocks are valid, and then from the incoming address, let us say the tag bit that is coming from the address is 0110. In the tag of one block of this selected set is 1001. That means it is not matching, this is not matching, whereas the tag in the second line is matching. So, that is correct. This means your data is located in this block, that is the second block of the selected set. Now, in the second block we can apply. So, when 1 and 2 happens, it is known as a cache hit, and once that is over, then we are going to extract the word. So, this 100 is the offset, that means from the 4th byte onwards you extract the remaining and we get the corresponding word that is requested by the processor. Now, this is the way how block identification is happening in the case of a set associative cache. So, this is a two-way associative cache. From the address CPU is giving, like previously mentioned, you have the tag portion, index portion and offset portion. With the index portion, you are going into the corresponding row. Since it is two-way associative, you have two different blocks. This is first block and this is second block. So, in both these blocks, access is happening parallelly. Both the tags are extracted, that is extracted. This tag is also extracted. So, tag of first block as well as the second block is extracted, and with the extracted value, the incoming tag that is coming from the address is compared there. It is also compared here. It will be valid only in one case. So, wherever it is valid. So, if it is valid or if the tag is matching in at least one of the location, then we call it as a hit. Once it is a hit, then using the offset of that corresponding block where the tag match happened, the data is extracted. That is called set associative. So, in the case of a set associative cache, indexing is done. After indexing, the tag matching in both the blocks are happening parallelly, and once it is a hit, the corresponding byte that is requested is being removed with the help of the multiplexer. So, this is the way two-way set associative cache works. So, it is just like two direct mapped caches working in parallel. The cache index selects a set from the cache. The two tags in the sets are compared to the input in parallel, and data is selected based on the tag result. So, the place where the tags are stored, it is known as tag array, and the place where data is stored, it is known as data array. So, if it is a two-way associative cache, we have two tag arrays and two data arrays, and comparison happens in parallel, and if it is okay, we call it as a hit, and based upon which block the hit occurred, the data is being removed. This is the case of a fully associative cache. This is the last category. None of the caches are generally in our common microprocessors. We are not using the fully associative cache. It will be either direct mapped or set associative cache. It is only in a theoretical principle where there is no index that is associated. We have an offset portion as well as a tag portion. There is no index portion associated with this. So, with the tag value, each of the block is compared, and wherever there is a hit, the corresponding data is extracted. Now, we will try to understand the design details of this indexing operation. Indexing operation is very important with respect to accessing of cache is concerned. Once CPU gives the address, it is from the index bits that we will try to locate our point of interest. So, here in this case, in this example, we have 5 bits used for indexing. So, these 5 bits can take a value ranging from 0 up to 31. So, I have total of 32 sets in this case. So, these 5 bits will uniquely identify one of these 32 sets, and that is being done with the help of a decoder of 5:32 decoder. So, smaller number of sets, less will be the indexing time, small will be the size of decoder. So, when you go to larger cache memories, the number of sets will be more, so the indexing time will be more. So, if you wanted to retrieve a data from cache memory very fast, cache memory should be having minimum number of sets. So, we have trying to connect this issue with respect to the speed up of a pipeline. We started our discussion in such a way that cache memory is used in the case of an instruction fetch as well as the mem stage of an instruction pipeline. In both these cases, we have to make sure that cache memory returns the corresponding word within one clock cycle, and that to happen, our cache memory should be having minimum number of sets. So, in your L1 cache, whether it is I cache or D cache, the number of sets has to be minimum such that our indexing time will be very less, and after indexing then comes the tag comparison, and then it is like the block offset extraction. So, all these things has to happen in one clock cycle. Now, we will see why are we using the middle bits for indexing, why are we not using the most significant bits. So, in our address split up, the first few bits, the most significant bits are tag, Next we have few bits, they are indexed, and the last bit is used for offset. Now the offset is nothing but they are the bytes within a block. So let us leave offset for the time being. Out of the other two, why are we use the middle bits for indexing? What is wrong if we use the most significant bits for indexing? So consider a cache memory which has 4 blocks. We can call the blocks as 00, 01, 10 and 11. Now if we use higher order bit indexing in the address, adjacent memory lines will have the adjacent memory blocks, adjacent main memory blocks, their most significant bits will be common. So when you map, if the indexing is based on higher order, they all will map into the same location. That means we cannot make use of spatial locality. That means when there is a request to one of the block, we bring it to the cache. The adjacent block also, if the indexing is in such a way that if you use higher order bits for indexing, the adjacent block in main memory should also be mapping into the same block. It will be in the same line. So the first block is replaced and second block is brought. Now third block also will be mapping to that. Fourth is also mapping to that. So in order to avoid that, we are using the next bits. So this is what is called higher order addressing. That means all the blocks in main memory, let us assume we have total of 16 blocks in main memory ranging from 0000 to 1111. Now if you use the most significant 2 bits for indexing, these are the 2 bits, and for these 4 blocks the most significant 2 bytes or 2 locations are going to be same. So they all will map to the same block in cache memory, whereas this will map to this block in cache memory, this is mapping to next in cache memory, and this is mapping to the other one in the cache memory. So when you have 4 cache memory blocks, it is these 2 bits that is going to govern where it should be mapped. So adjacent blocks are mapped to the same one. That means we are not making use of spatial locality. Now this is what is called higher order bit addressing. Now if you use middle order bit indexing, then consecutive memory locations may be mapped to different lines in the cache. So it is a better use of spatial locality. This is what we can see. If you are using the next 2 bits, the least significant bits apart from the offset, this is 00, that will be mapped to this line in the cache. 01, that is mapped to the next line in the cache. So this is 00, this is 00, this one is 00 and this one. So these are the 4 blocks that gets mapped into the same location. From the color you can see this is one, this is same color. So that means adjacent locations are getting mapped to adjacent locations in the cache memory. So today, to just summarize what we learned today, we were trying to see what is the role of cache memory. Cache memory is trying to give an illusion that we have unlimited amount of fast memory, and it is an interface between your processor and your main memory. Transfer of data from cache memory to CPU always happen in terms of words, whereas transfer of data from main memory to cache memory happens always in terms of blocks. A block consists of multiple words. We learned about what is the concept of a hit or a miss, hit rate and miss penalty, and we are trying to address the design issues in cache. Today we were focusing our attention to 2 of the design issues. One is called cache placement. That means once you get an address from CPU, how will you know that whether it is present? That is called cache identification. And once you get an address, how will you bring that particular address from main memory into cache? So we learned about cache placement with direct mapping, set associative mapping and fully associative mapping, and we learned about block identification and what is the role of this indexing, why we need to keep caches as simple, the number of sets should be as minimum as possible. So with this we conclude our first lecture on cache memory. On subsequent days we will be focusing our attention into slight optimizations in cache memory. There are 2 more design issues, replacement and write strategy to be covered, and then we will focus on optimization aspects of cache memory. So we will be also uploading the tutorial sheet for this week, the assignment sheet for this week. Kindly go through them such that you get idea about how to work with this. So thank you.